Welcome to the Ute Corporation's presentation on the economics of structural lightweight concrete. In this presentation, we will discuss what structural lightweight aggregates are, common applications for structural lightweight concrete, and where the design engineer will find the economics of its use. My name is Jeff Barrick, General Manager of Ute Corporation, and I would like to thank you for taking the time to join us. Lightweight aggregates have a long history of use as a concrete material. The Roman Empire, as it expanded, would use lightweight aggregates whenever possible, sometimes hauling them many miles just so they could use them in their concretes. They understood the reduction in density would allow them to create the structures that they had envisioned. So what is a structural lightweight aggregate? They can be broken down into three categories: a natural lightweight aggregate, a byproduct lightweight aggregate, or a processed or engineered lightweight aggregate. All must meet structural performance criteria. This criteria is found in either ASTM C330 or AASHTO M195, whichever standard is relevant to your project. Natural lightweight aggregates are all volcanic in origin. The two most common are scoria or cinders, shown here on your left, or pumice, shown here on your right. These materials, being naturally occurring, can show fluctuations in density and also alkali silica reactivity as you move through a deposit. Byproduct lightweight aggregates, commonly blast furnace slag from the iron industry or bottom ash from coal-fired power plants, are found regionally throughout the United States. It should be noted that changes in raw materials or in fuel sources can affect the performance in concrete, especially in staining or pop-outs. Processed or engineered lightweight aggregates, commonly known as expanded shell clay or slate, ESCS, are the only lightweight aggregates that are produced specifically for use in concrete or construction applications. The ESCS industry began in the early 20th century when a brick producer out of Kansas City named Stephen Hayde began to realize and understand the benefits that a true structural lightweight aggregate would offer to concrete. He was granted a patent in 1918 and began selling the material under the name of Haydite. The use of structural lightweight concrete began to gain in popularity during World War I. With the lack of steel due to the war effort, shipbuilders began to look to alternate materials such as concrete for the building of ships. Structural lightweight concrete, with its lower densities and high levels of performance, proved to be a valuable option. The first commercial facility dedicated to producing expanded shell lightweight aggregate began operating in Kansas City, Missouri in 1920. In 1922, the first lightweight concrete building in history was built at Westport High School in Kansas City, and by the end of 1929, the first major project, owned by Southwestern Bell Telephone Company, which was a 14-story addition to an existing 14-story building made possible only by the use of structural lightweight concrete, was completed. The raw material for an expansive lightweight aggregate, be it shell, clay, or slate, may look very different geologically, but when looked at through its mineralogy, you'll see that they all have to fit into a very specific window to actually be expansive. Once an expansive deposit is found, it may be soft enough to simply quarry with heavy equipment, or it might be hard enough to where an operator will need to use explosives and blast. Once the material is extracted from the deposit, it's taken to the process facility for raw processing. In raw processing, the expansive material is crushed and screened to the desired size. This size will vary depending on facility and even raw material. It is then stored in silos or tanks which feed directly into the kiln. The raw feed is then fed into the kiln. As the feed travels the length of the kiln, it goes through many processes and phase changes. First, there's the removal of moisture, then you get into the calcining phase, then as it reaches the burn zone, the material becomes red hot and plastic, where the gases that are created internally trying to escape cause the material to expand or bloat. The operation of the kiln is computer controlled and continuously monitored 24 hours a day, 7 days a week, 365 days a year. In the burn zone, the temperature is maintained at approximately 2000 degrees Fahrenheit. Once the material drops out of that burn zone and into the cooler, it is now a vitrified ceramic aggregate. The encapsulated gas voids attribute to the aggregate's density, absorption, thermal, and acoustic properties. The hard ceramic matrix is what gives it its strength. Together, these two properties are responsible for ESCS materials' consistent and exceptional performance in concrete. Lastly, the material is sent to finished processing. This is where the material is screened to its desired size, and quality control measures such as grading and oven-dried densities are performed to assure compliance to specifications. This is all completed before any material is ever sent to the end user. So what is structural lightweight concrete? ASTM C330 and AASHTO M195 both have criteria based off of a prescriptive mix that concrete made with these lightweight aggregates must meet to be considered a structural aggregate for structural lightweight concrete. So why do structural engineers use structural lightweight concrete? Simply put, design flexibility. And along with that design flexibility, they also find economy. So where does the design engineer find the economy? It'll be found in a few different areas. Structural efficiency, the number one thing, is the reduction in dead load. Reduced dead loads are going to offer longer spans, increased width, thinner floor sections, reduced substructure, thermal and acoustic efficiencies. In construction efficiencies, less transportation costs, less site congestion, and better crane efficiencies will be seen. In structural performance, the design engineer will find economy in structural lightweight concrete's performance in fire resistance, seismic response, retrofit flexibility, and superior concrete durability. When looking at economy of design, a holistic cost analysis process should always be used. Though structural lightweight concrete may carry a 25 to sometimes as high as 75% cost premium over normal weight concrete, the overall savings to the whole project in design will far outweigh these costs. Concrete is just a small portion of the total project costs, and the reduction in other areas will always offset the cost of the lightweight concrete, or it simply will not be used. So let's look at some applications. Structural lightweight concrete and bridge decks. Historic bridge retrofit is an area of common use for structural lightweight concrete. If you have a historic bridge that needs to be updated to handle today's traffic volumes and traffic loads, structural lightweight concrete is the preferred method to be able to go in, replace that deck, and keep the historic structure. ABC, or Fast Track Bridge Design, is another design tool that's gained popularity across the country. The use of structural lightweight concrete on the bridge decks has also gained in popularity. Not only is the reduction of dead load from the deck help in the ease of move of the bridge section, but in some cases a full line of girders have been able to be removed due to the additional width available because of that reduction in dead load. This chart shows the additional spacing that may be achieved with various structural lightweight concrete and normal weight concrete combinations in bridge section design. This is one area where the design engineer may look for the additional economy that structural lightweight concrete may offer. Structural lightweight concretes have been used for many years as a solution to design challenges. In 2013, the Transportation Review Board, or TRB, issued a full report on the use of structural lightweight concrete in bridge girder and decks. This report is available online or from any ESCS producer. Concrete on metal deck is an area where structural lightweight concretes are commonly used. When structural lightweight concretes are used on metal deck, it offers the design engineer many areas of additional economy. When structural lightweight aggregates are properly handled and the concrete mixture designed within the recommendations of the ESCS supplier, placement of the concrete on a metal deck will be similar, if not exactly the same, as any other concrete that might be used. When the design engineer specifies structural lightweight concrete on a metal deck, he affords himself many areas of economy. The reduced dead loads will offer savings in steel in smaller columns and beams and less reinforcing steel. They'll also see savings in excavation due to smaller foundations. The thinner fore sections to achieve a UL or fire rated assembly means less overall concrete on the project, and no spray-on fire retardant will be necessary to meet many of the UL assemblies. Prestress concrete is another area where structural lightweight concretes are commonly found. Not only does the reduction in dead load offer a potential for longer spans or increased widths of a pre-stressed member, but the reduction in transportation is far and away the biggest area of improved economy. By being able to load more pieces for every load leaving a facility, transportation costs can be dramatically cut. This also translates into improved erection efficiencies and less site congestion. The economy found in precast concrete and concrete masonry through the use of structural lightweight concrete may be very similar to those found in pre-stressed concrete. Transportation, erection, and installation costs are all areas that may benefit from the use of structural lightweight concrete. In some design, thermal and acoustical properties, as well as concrete durability, may show some economy, especially if looked at through life cycle costing. So in summing it up, the economics in these applications, as found in all, are going to come through the reduction in dead load. This relates directly to less transportation. Yes, you will see some longer span opportunities or increased widths, which may mean less members. You get some erection installation efficiencies. You may see some thermal and seismic or acoustic response, which show cost efficiencies and more economy in life cycle design. One last application I would like to touch on are what we call specialty uses. These concretes are going to be exposed to harsh environment, such as F-35 vertical takeoff and landing concrete pavement, refractory concretes, which are exposed to high temperature, concrete docks or piers, which are exposed to harsh marine environments. Structural lightweight aggregates and structural lightweight concretes have been used for years in these applications. They perform very well. Much of this is due to the aggregates properties and the cement paste properties being very closely related, having very similar coefficient of thermal expansion and an improved contact zone between the two. And finally, a few bits and pieces I'd like to touch on, not necessarily related to economics, but they're topics that always come up with design engineers, contractors, finishers, people that we deal with every day in the market. Finishing structural lightweight concrete. Structural lightweight concrete that you'll find in the field is almost always air entrained. That is to economize the mix and get the weight down as economically as possible. Air entrained concrete has specific recommendations and guidelines for the finishing process. You can find those in ACI 302. Lightweight concrete does not blister or delaminate any more than any other Air and trained concrete will, as long as the procedures are followed properly. Make sure that your finishers know that it is air and trained, and make sure that they have experience working with air and trained concrete prior to the project or any concrete placement. Floor drying or moisture vapor emissions is another topic that does come up from time to time. Structural lightweight concrete may take slightly longer to dry than a normal weight concrete, but has not been shown to be significant. There are many other reasons that moisture may be present longer. It could be due to not protecting the concrete, allowing it to become re-wetted. It could be the use of some type of a curing compound. There are many ways to check this out in the field. The one thing is that you need to make sure that everybody's on the same page. You should have a pre-pour meeting with the contractor, the design engineer, the ESCS supplier. You might even need to go as far as having a dehumidifier put in place or use a more expensive adhesive if it's a fast track project. So that brings us to the end of our presentation on the economics of structural lightweight concrete. And again, I would personally like to thank you all very much for taking the time to sit down and join us for this presentation.